Okay, we should probably move on to the third of the morning's talks, and it's kind of nice. It's a 1-2-3 punch in that the first one is a survey telescope that we're essentially leveraging the great survey output. Shelley talked about a specific kind of bespoke telescope that's being built for this purpose, and the third parameter are other experiments or telescopes for other purposes that we can piggyback on and really leverage. And so Francesco Longo is going to talk to us about the Cherenkov telescope array, which is coming along. So please go ahead.
Yes, thanks for the invitation to this very nice workshop. And I should say that I am quite new to these topics. So luckily today, and there is also Jamie here, who made quite a lot of work on this topic earlier. So he might also comment later on more than me on the usability of the Cherenkov telescope for this optical setting. What I'm going to share, you can see the full slide, in full screen mode.
Okay. Yeah, we're actually seeing it in the app. Is there any way to make it full screen?
I'm moving. Is that okay? Let me share, resume. Okay. So let me stop again and share again.
Yeah, sorry. Maybe when you get the full screen mode, it has to be restarted.
So, okay. Now you can see that. Okay.
There, perfect. Thank you.
Okay. So we'll discuss about the transient searches with the Very High Energy Telescope, and I will start basically from the telescope I am already working on, which is the MAGIC telescope, and then move from the experience from MAGIC to the transients program that are available in the CTA. So basically, this small seminar will, let's say, contain few information. So I will tell you how this telescope work. Maybe some of you already know this imaging atmospheric Cherenkov technique that is, let's say, quite successful after, let's say, several years of testing and improvement. And nowadays it is currently showing its full potentiality. And it will be still improved with the next generation Cherenkov telescopes. Then I will tell you a few words about this transients program, taking as an example the discovery of very high energy emission from gamma ray burst. This is a topic that I know better. I am a gamma ray burst scientist since the beginning, so I know this topic quite better. But showing that, you will see the potentiality of this telescope also for other kind of transients. And this will be the third part of my small discussion. I will discuss how MAGIC can do transient searches. So based on this experience, there is similar projects in all the other major Cherenkov telescope operating, like Veritas, that you might know better, and HESS as well. So based on this experience, the Cherenkov telescope array, which is currently being built, will have also a transient key science project. And at the end, we'll conclude with the new era in very high energy transients with just a few highlights and the possibility of using this telescope also for SETI searches. So this is what I'm going to tell you today. So basically, the imaging Cherenkov telescope, you have the very high energy gamma rays starting at tens of GeV or so, that converts into an electromagnetic shower in the top of the atmosphere. These particles are, let's say, superluminal in the atmosphere, so they emit, as it was discussed before, a flash of a few nanoseconds of, let's say, light, Cherenkov light, because they are superluminal. And this very huge telescope on the ground, they make an image of the atmospheric shower, and they image that on the camera in order to get the direction and of the shower. From its shape, we can detect also the nature of the event, if it is hadronic or leptonic in origin. And also, given the amount of light that is collected, we can detect the energy of the possible shower. So the threshold for a single gamma ray entering there is around 10 of GeV, and the Cherenkov light is in the optical and near ultraviolet light. So these are pointing instruments. They have a good angular resolution for gamma ray astronomy, I mean, which is 0.1 degrees. For optical is quite a lot, but for gamma rays, it is very nice. So they have a huge effective area for gamma rays, so 10 to the 5 square meter on the ground. So MAGIC is one of them. it is consisted of 2 telescopes in the Canary Island of La Palma, where other telescopes are built. This is the Gran Canarian telescope, GCT. This is the Italian Telescopio Nazionale Galileo. And these 2 are the 2 MAGIC telescopes, MAGIC 1, which was built first in 2004, and MAGIC 2, which was built in 2009. And they have 2 photomultiplier based optical cameras. These telescopes are 17 meters in diameter. So there was quite a lot of activity during the years to improve its sensitivity. You see here in the energy threshold. And this sensitivity was improved thanks first going to one single telescope to mono, from mono mode, sorry, to stereo mode, so adding a second telescope, and then several upgrades in the cameras. Okay, the camera that the PMTs and the data acquisition system improved, and nowadays we reach this current very nice sensitivity. So we have a good sensitivity for short time scale related to transients, given the very fast, let's say, optical digitizing system that we have there on the cameras. So the gamma ray burst was always one of the key science topics for MAGIC. They were built as lightweight, they are 70 tons, and they can have a fast repositioning mode, so up to 7 degrees per second. So if a gamma ray burst happens, they can move and steer rapidly to the location of the GRB to search for very high energy emission. And this started since the beginning when the MAGIC was still in monophase, okay, with one single telescope. So for example, this was the GRB of 13th of July 2005, so 16 years ago, where you see that following the alert from Swift BAT, MAGIC was there after 30 seconds or so. And of course, we can just put upper limits there, and we extrapolated the spectrum that we had. Fermi or Agile were not on orbit yet, and so we didn't have any other information apart from the Swift detection. And so these are upper limits that are consistent with the extrapolation of the same spectrum seen at low energy. But this shows that these telescopes are really designed to do fast repointing and get very fast, let's say, analysis of the data. So to get the transients, which is the aim of this, let's say, transient program, we designed an autonomous alert system that was originally designed for gamma ray burst. Was recently adopted by Alessio Berti, who presented there, and the original designer was Alessandro Carosi. They and Nicola Galante, that some of you in Veritas might knew already. He went to US and worked with Veritas for some time. So basically, this gets the gamma ray coordinates network information, the information that something happening in the high energy sky. It gets the notice. It gets an alert validation. It's, let's say, calculating the path from the telescope where, let's say, the telescope is pointing, the position of the moon, and so on and so forth. So these then calculate if it is observable or not. Let's say, we notify the user and then interact with the central control system to get the repositioning of the telescope. And then the telescope are immediately repositioned in the due time. So this was recently adapted to neutrino and gravitational wave fast alerts, and the protocol on VO event is currently being implemented. So this allowed MAGIC to detect for the first time a gamma ray burst in 2019, in January 2019. And let's say we got more than 20 sigma in the first 20 minutes, and this was observed about less than 1 minute after the Swift alert. So this was quite nice. And this is shown here. Let's say the alert was received at this time. The tracking, let's say the system reacted, let's say after some time of the alert due to the calculation of what I said before, and then the DRQ started a few seconds after, and then after the, let's say, the relaxation of the movement of the telescope, we could observe, and the high flux that was there, we could observe after 52 seconds, and we observed this very nice declining flux rate. This allowed for the first time to get these very nice spectra of GRB, let's say, highlighting the 2 components from the synchrotron and the Invesconton one. So this is, I think, an historical measurement. This was the first time that the gamma ray burst was announced to be detected at very high energy. There were several searches by all the other telescopes, and indeed has later on in the same Nature issue published another GRB that happened 1 year before, that was announced in the first CTA symposium in May 2019. And nowadays we have more than other 2 bursts that are firmly detected. So we have 4 bursts detected at very high energy. The MAGIC transient program is not only for gamma ray burst, it is for other types of sources. So this is the other gamma ray burst that was detected in 2012. So we have a gravitation wave counterparts, and we are implementing the scan procedure over the whole error box. We have neutrinos. We have new channels that are being implemented, and we are searching for alerts, and the MAGIC detected one counterpart from one very high energy neutrino from IceCube. But what might be of interest for you here in this community is that we search also for fast radio burst, and our, let's say, organizer of this seminar was actually involved directly and heavily in this search, because we have a program to search simultaneously with the radio some fast radio burst, and particularly for this one, 121102, which was the first one that was repeating. We had a coordinated campaign with radio telescope, and we have observed simulation both in very high energy using the Cherenkov technique and also in optical. In optical, why? Because it's the central part of the huge mirror of, let's say, the huge camera, sorry, and the central part, sorry, of the telescope. There is an optical pixel that can get let's say, get the optical signal, not only the Cherenkov one. So we installed a new optical pixel in MAGIC 1, while this one was done with MAGIC 2. John can comment later on if needed. So these are some results on other GRBs. You see how fast we can repoint down to 30 seconds or so. I will not go into the detail of that, but I want to say a few words about the other alerts. We received an alert on neutrino, we pointed to that, and we discovered the very, let's say, this is the error box. We got some alerts also from Fermi, and we got the detection of this very high energy neutrino, and the following up campaign was conducted also with Veritas and Hess and all other, a series of other telescopes. And this was the first time that the very high energy gamma ray is coincident with the high energy neutrino. Last but not the least, the fast radio burst that I told you, this is was associated with, let's say, located in a dwarf galaxy at this redshift. It was searched in all the other counterparts, and we can put constraint both in very high energy and in optical. So I will concentrate more in optical, since this is an optical SETI workshop. This is reported in this paper, accepted in 2018 in monthly notices. And there are reported these points. This is the central pixel around the fast radio burst. You see the signal that is recorded. There is, let's say, some noise on that because it was optimized for pulsating searches, not for single searches. And in that period, we got a flare before, which was not associated with any other signal. It might be meteor or whatever, but this shows the capabilities of this telescope to get this very fast optical signal that might be of interest also for SETI signals. These, the details are reported here in this paper, and in case John can also give you more details on that. So the details on how MAGIC is sensitive to millisecond duration optical pulses was reported by Tarek, John, and other authors in these in the International Cosmic Ray Conference in 2017, and this is the paper of the, let's say, the central PMT of MAGIC 2 cameras. This is sensitive to short 1 millisecond to 1 second optical pulses. Originally was developed for Crab pulsar searches, but it is being used for fast transients. So now let's go to CTA. CTA will be the next generation imaging Cherenkov telescope observatory, going from 20 GeV to 300 TeV. It will be a first open observatory in the field. It will have 2 sites, one in the Canary Island near MAGIC, the other one in Cerro Paranal in Chile. And the CTA consortium, to which myself and Jamie are belonging to, is responsible for the concept and the design of CTA, while the observatory will be the manager for operating and building the observatory itself. So there are several design drivers. Let me say that the transients are the key of them. So the rapid slewing, the energy is going down to 20 GeV. the possibility of getting full sky coverage. These are always needed, or the wide field of view to get more transients. These are a lot of transient science can be done with CTA. So to build that, we are thinking to have 3 types of telescopes. We have the large size telescope of 23 meters, the medium sized telescope of 12 meters. This was still the 1 meter design. There is another design that is being currently proposed with the 2 telescopes also for the medium sized telescope, and 1 small size telescope of 4 meters, where recently the 2 mirrors geometry was decided. So CTA performance is improving in these energy ranges by a factor of 10 and more in the core business, so around 1 to 10 TeV. But also here at low energy, we have quite an extension with respect to MAGIC, Hess, and Veritas. So I think this will be really a transient telescope recently. Very, for sure it will be like that. Why? Because we needed to test extreme environments like neutron stars, relativistic jets, stellar explosions, which are really needed, let's say, transient sensitivity. Also, the same is true for some fundamental physics like Lorentz invariant evaluation or primordial record searches and so on. So the transient goal is one of the key science topics of CTA. And indeed, the CTA consortium has put forward several key science projects, and one is the follow-up of transient and multi-messenger events. So based on the experience that was gained by the previous Cherenkov telescope, and MAGIC was one of them, there are several of them, and particularly they will be beneficial from the huge sensitivity with respect to Fermi at low energy. Fermi can cover up to, let's say, hundreds of GeV, but the flux sensitivity of CTA, given the much larger effective area due to the let's say, the cone of the shower, that when the shower is much more sensitive at, let's say, transient. So if we can able to point there in few minutes or 10 minutes, we can detect much fainter transients. So this is our goal also for fast radio burst. So we will have an on-site analysis. We can get alerts and TOs. The observatory schedule control will analyze these, let's say, these alerts, and will decide whether to point or not. And if there is something, a real-time analysis will work on that, and with 30-second latency will alert other telescope that something was going on in the TV sky. So the key science project will have several, now I'm going out of time, but these are some of the questions that can be answered by the key science project in transient. So some of them are, for example, the CTA in gamma ray burst, where we are looking around to develop the previous estimates based on some theoretical population and theoretical emission for the prompt and for the afterglow. And we are studying now the CTA detections possibilities. More details will be given in future ICRC and future conferences. And the same is true for CTA in gravitational waves, where we will do a tiling with using CTA to get the huge error box to get a possible counterpart there. And last but not the least, the neutrinos, where also we are adopting some, let's say, theoretical motivated emission of gamma rays to get the number of possible counterparts to neutrinos. So there are several other topics. One that is not yet fully explored is the fast radio burst, that had quite a nice confirmation later on that might be associated with magnetars. So for example, this one, it is a Nature paper of last year, where there were a fast radio burst connected with the X-ray. So if there was a program to repoint on that and let's say following, and if we were following one of these, this was not a repeating one. So we need to fast react and see if other of these will be available later on. So now let's come to the possibility of using TV telescope. Maybe yesterday already was discussed something. This dates back to some ideas in 1981 or 2001, sorry, by Eichler and Besking, optical set with their Cherenkov telescope, to use these to monitor a series of stars with the distance of 100 parsec up to nanosecond pulses of magnitude 6 or brighter. Then Jamie did, presented that in the 2005 ICSC conference with the searches of optical set with the imaging Cherenkov telescope, using the possibility of imaging that, not just collecting the Cherenkov light. And I think that this is something which is very nice, and I'll point you to his publication. Last but not the least, the Veritas collaboration searched for brief optical flashes from these F-type stars. That was an exceptional target for SETI observations. So you might see that these telescopes are already searching for that. To my knowledge, I might be wrong, but again, Jamie can comment, there is not yet an official program for that, but since CTA is an open observatory, I think that the community might try to get something to ask them. There is a group working on optical interferometry that you can work on, and the SETI program might be improved given the large number of telescopes and the spread that where they will be built. So the conclusion that CTA will open a new era in new very high energy astrophysics, having a rich science program with large new discovery space. And maybe this optical SETI will be one of them. Why not? Because the optical telescope, the optical properties of this Cherenkov telescope might be best suited given the very huge collection area and the possibility of getting these nanoseconds pulses, as they are needed for Cherenkov telescopes, but they may be used also for SETI searches. And the full exploitation requires multi-wavelength and multi-messenger synergies. And so I think that hope to see you soon with the full telescope installed. Maybe not so soon there in the south, but surely in the north we will have the 4 LSTs and some MSTs. In the south we will start with the MSTs. You see here there is the new second design of MSTs and some full small size telescope all over the place in the Paranal Desert. So see you soon with the data from the CTA. The prototype are being built and commissioned.
Terrific. Thanks, Francesco. That's great. I will say that the Cherenkov telescopes have the most beautiful secondary support legs. They look like they're almost flowers kind of opening up.
Yes.
We do have some time for a few questions if people want to ask any.
I've got a question, Dave. I put a hand up.
Yeah,
Could I ask
sorry,
it?
Paul. Yeah, it's in this view, I can't see the full group. So go ahead, Paul.
Yeah.
Sorry.
Okay, yeah. Well, just maybe you answered this, but I know that in things like Veritas, the trigger discriminates against a flash that's seen in a single pixel because it's interested in things that are spread in sky. Will the CTA overcome that limitation, because that limitation is obviously an anti-SETI trigger?
No, this is what I said. I think I don't know whether there is already a group working on that. The trigger of the array will need, there will be a trigger on single telescope, of course, and then the stereo trigger combining all the other telescope will be needed because, of course, you will have them. We will need that to trigger on Cherenkov telescope, but each single one will have its own trigger. So I think that in this case, we might work with the people working on the optical and see if this will be possible. As I said, I am quite new to that, so maybe Jamie, who was the science coordinator, might know better than me. But I invite the community in case to contact the people working on the optical group. I don't know whether these consortium group are already public or not. Also, I ask Jamie for confirmation, and I can point you to who is actually the responsible for that group.
I guess just the question is, within one telescope, will it trigger on a single pixel, or does it reject single pixel within one telescope?
Single pixel, I think that you need that it is higher than a certain threshold, and then normally you have also to have some bright pixel nearby. But of course, I think it is a matter of the threshold, and I know how the trigger on the different telescope is being built. Okay, this is again something that might be asked. I know how, for example, in Magic is done. Magic have, for example, as I said, you have the single PMTs, the trigger, and then the first one requires at least some triggers nearby to go to eliminate some, let's say, fluctuation of the night sky background or other bright objects.
All right, thanks, Jamie. I saw you popped in. Did you want to say?
I'd just say Paul's identified the big challenge for doing this with CTA, which is, as you say, our trigger is designed to look for extended objects, and a point source will not trigger. We have brought this up within CTA as an issue, and I think people are thinking about it, but it's challenging to, how do you the only way you could really design an instrument to do that and keep the background reasonable would be to have a hardware single pixel coincidence between separated telescopes. I think it's something we're going to have to push on if we want CTA to do optical SETI. There are possibilities to do it with certainly some of the camera designs, and feedback from a large group like this explaining that the science is interesting is one way that we can push on that. So yeah, David and I and Francesco and others in CTA will keep an eye on it.
Yeah, I think one of the camera designs in particular would allow single pixel triggering at an arbitrary threshold. So in principle, you could choose a threshold that would be high enough to get an acceptable rate that way, and then look offline for two telescope or multiple telescope coincidences. But that's the flash cam for the medium-sized telescopes. But the other designs typically have fairly deep at the hardware level multiple pixel requirements.
All right, well, great, thanks very much. I think we're now scheduled for a break. It does say 15 minutes, but it also says 5 after the hour, so maybe we can start back up at 5 after the hour and go over some basic machine learning, and then try to actually have a workshop discussion on furthering collaborations and how this diverse group might want to go forward with this. So we'll see you all in about just over 10 minutes.
Okay, bye-bye. Ciao.
Thank you.